Okay, welcome back everybody. So this afternoon, I'm going to start off looking at vectorization, and then we'll finish up with memory optimizations after that. Okay, so here we're talking about vector instructions and essentially how to persuade the compiler to generate them. So just by way of introduction, have these modern CPUs can perform multiple arithmetic operations on each cycle, also multiple loads and store operations as well. So use a special vector or SIMD instructions to do that. So there's various, essentially a vector set, vector extensions to instruction sets like SSE or AVX, which support this. So these typically operate on a vector of data. So this will be maybe 2, 4, or 8 double precision floating point values. And so this can potentially, particularly for floating point operations, this can enhance performance. If we have nested loops, then usually the compiler is only going to be able to vectorize one of those loops, and for the most part, compilers will only really consider the inner loop. In some simple cases, they may be able to vectorize an outer loop or do loop interchange and so swap the order of the loops and then vectorize the inner loop. Okay, so a little bit more detail about how this works. So basically, doing this, when we're doing vector operations, vector instructions, we're doing the same operation on same arithmetic operation or same memory operation, loads or stores, on multiple data items. So this requires special hardware support in terms of wide registers. So there has to be, you have to have, the chip generally has vector registers, which can hold these multiple in multiple values. And modern hardware, if you're not generating SIMD instructions, then you won't be able to approach the peak floating point performance. So there's a factor of 4 or 8 in the floating point peak floating point performance of the chip that comes from using vectors. So in terms of x86 SIMD instruction sets, the old ones, so SSE, so 128-bit registers, AVX 256-bit registers. So basically have a SIMD, a normal serial instruction would take just a single 64-bit floating point value, add that to another one and produce a single 64-bit result. Whereas a SIMD instruction can take, say, 4 double precision words and add those to 4 corresponding double precision words and produce 4 outputs, and this is all done in a single instruction and execute those adds executed in parallel in the hardware. So Rome processor has AVX 256 vector units, so they are symmetrical units, so they're based, but only one of them supports some of the legacy stuff. So that's not really important. And the vector floating point instructions typically have a latency of 6 clock cycles on row. So our optimizing compilers will try to use vector instructions, but that relies on having code that is vectorizable or a form that the compiler can convert to being vectorizable. Compilers vary a bit in their ability here. Some compilers are better at this than others, but there's some general guidelines about what's likely to work and what isn't. It's, compilers can always surprise you by failing to vectorize even when you think you've met all the right conditions. So essentially, when does the compiler vectorize? Well, what can be vectorized? Just loops, okay? As I said before, it's usually only one loop in the loop nest is vectorizable, and that's normally going to be the innermost loop. So yeah, how do you know? Okay, so one thing you can do is look at the compiler output listing, and we'll talk about that in more detail as to what to look for from various different compilers. Or you can look at the assembly code and see whether the assembly code contains the appropriate vector instructions. So whether it's using the right whether it's using the right registers or generating the instructions that start with a V, for example, are the vector instructions. So what do we need in order for a compiler to have a good chance of generating vector instructions? Well, loops need to have a determinable trip count, at least determinable at runtime. It doesn't have to be compile time determinable. So that rules out a lot of while loops. The loops can't contain any function or subroutine calls unless the call can be inlined by the compiler, or there are some cases, for example, you can for certain classes of functions which are basically don't have any side effects. They can be vectorized, but you typically need to point the compiler at them, especially, and say, please generate a vectorized version of this function call. Things like mass library functions are usually okay. So most compilers come with a vectorized maths library. GNU compilers don't necessarily, but most other compilers tend to have vectorized versions of maths libraries available, so they're okay. The loops mustn't contain branches or jumps. Some patterns like guarded assignments might be okay, though it can be dealt with. So if essentially the condition is if the evaluation of the condition is itself vectorizable or can be turned into guarded vector instructions, then that's okay. So patterns like if AI is not equal to 0, then do something. That kind of thing can be dealt with. It may not be especially efficient. So if if the condition is frequently false, then you are basically taking up slots in those instructions which don't do anything. But they are that kind of pattern can be vectorized. The loop trip counts for good performance, then they should be a multiple of the vector length, unless they're very long, in which case it doesn't really matter, because the loop is going to be executed in chunks of iterations equal to the vector length, and there will be, if there's any remainder at the end, then those iterations have to be done with plain old serial instructions. So if the loop's short, then it needs to be a multiple of the vector length. If the loop's very long, then it probably doesn't really matter if there's a few serial instructions going on at the end. Okay, what else? The loops mustn't have any dependencies between iterations. So patterns like reductions are usually okay. The compiler can handle those, or can usually handle those automatically. So formally, a reduction pattern where you're summing up into some scalar value is a dependency, because each loop iteration does require the value from, does in principle require the value from the previous one. But the scalar can be split up into a short vector, and then there'll be some code at the end that adds up the partial sums. Another one that compilers can struggle with is induction variable. So induction variable is basically a scalar which is incremented by a constant amount inside the loop. So if we're then using that as a, for example, if this is then used as an array, as an index into an array, so patterns like this can be problematic. We can use things like the restrict keyword to try and convince the compiler that there aren't any dependencies. Otherwise, it might make worst case assumptions about pointers, which we'll come on to again later. But in general, we may need to tell the compiler if it can't work it out for itself. If the compiler detects a dependency where there actually isn't one, then we might need to explicitly tell the compiler to go ahead and vectorize anyway. Aligned data is the best for options. So it's best if our data is aligned to the appropriate byte boundaries. So for example, AVX vector loads and stores are most effective and most efficient when we're dealing with when the first element of the vector is aligned on a 32-byte address. So either need to let the compiler do its own alignment, or we force the alignment and tell it what it is. And also for maximum efficiency for loads and stores, it's best if we have unit stride through memory. Non-unit stride can be coped with, but it requires gather and scatter operations to collect memory from scattered addresses into a vector register, and then store them back out again into non-contiguous locations. So non-unit stride accesses can be vectorized, but they're typically less efficient than unit stride. So what do we need to persuade the compiler? So for the Cray C compiler and AMD compilers, generally need, so optimization is, we need optimization enabled, which we generally would have by default. It needs to know which hardware it's compiling for, so need to set the march flag appropriately. On ARCHER2, that's automatically added for you. You can turn it off if you want to. So this is useful for checking to see whether vectorization is giving you any how much performance gain it's getting you. It's can be instructive to see what happens if you turn it off. Is it actually making the performance a lot worse? In which case you could say you might be convinced yourself that you're getting some benefit. So there's various ways that you can get the compiler to tell you what it's done. So there are these flags that you can pass. This is for the Cray C compiler. Other compilers, so Fortran compiler, so minus h list equals a, tells you stuff. GNU is a bit more difficult in the sense that the diagnostic flags tend to produce a lot of information in a form that's not very easy to digest. But there are GNU compilers do have flags to dump various diagnostics. Yeah, so check what it did. I think that's all the previous ones. You can also get some clues from CrayPat as well, from the hardware performance counters. So if you look at the floating point instructions, it's a bit messy, but if you look for, if the ratio of operations to instructions is bigger than 1, then that's a sign that the vectorization has succeeded. Okay, so for if you have double precision floating point values, then if it's generating all AVX instructions, you would expect, or you'd hope to see a ratio of 4 operations per instruction. There's various other GNU options which you can try. So what happens if the compiler didn't succeed? What can we do? Okay, so do loops have dependencies? So is information actually being carried between iterations? So this kind of pattern, reduction patterns, actually is, if that kind of thing is happening, then you have a problem. You can, if it really doesn't have dependencies and the compiler has failed to spot that, then you can just go ahead and tell it's safe to vectorize. Otherwise, you might need to rewrite your code without dependencies. So things that you can do, we'll look at an example in a minute. You can promote loop scalars to vectors, can sometimes help. Again, for induction variables, so these where you have a constant, something that's incremented by a constant, you can replace that with a direct computation based on the loop index, which removes the dependency. If possible, you could try and move if statements are a problem, try and get those out of the inner loop. So that might require some loop reordering or other restructuring. Otherwise, or you might need some. You can create temporary vectors and compute the outcome of the if statement. Compute the outcome of a condition over the whole loop. So you do that as a separate loop, and then use the values inside the loop, for example, to avoid having the condition pattern. Oops. So what other things can compilers have problems with? Okay, loops with explicit pointers, liable to be a problem. Non-unit stride loops. So saying that they may deal with those, but they may not be so very efficient. If we have, odd patterns of memory accesses, that can be problematic. Unaligned accesses, or accesses where the compiler can't figure out the alignment. We'll come back to that in a minute as well. Yeah, I mentioned conditionals and dependencies. Okay. So you can have problems with, if you have indirect addressing, for example, so this kind of thing is a problem. So if we have, if J is basically, J is used to index an array here, if basically J comes from is a lookup into an array, then the compiler simply cannot know that all the J values are different, for example. There's no way for it to figure that out. You as a programmer may know that's true, in which case you can say that, okay, you can tell the compiler that it's safe to go ahead and vectorize. Okay, so how do we do this? How do we help the compiler? How do we tell it its loops are independent? So I'll talk a bit about compiler-specific things first, and then at the end we'll talk about the more portable versions that are now part of the OpenMP standard. So, for example, for Cray C compiler, it's basically Clang pragmas. You can say Clang loop vectorize enable, or basically for the Fortran compiler, you can have the ivdep directive. You also need this flag on. You also may need this flag on the compiler. You can use restrict keyword to say that to guarantee that different pointers don't never point to the same place. Align your arrays to cache line boundaries, and so again we'll talk about how to do this in a minute. And then also tell the compiler that your arrays are aligned. So maybe one or other of those, maybe, or both, may be necessary. And try to make loop sizes explicit to the compiler. So for small loops, it will help if the compiler knows how big they are. So here's an example where that has, does the compiler recognize the size of the vector? That is a good question. I don't know the answer to that, I'm afraid. My guess is probably yes, but I couldn't be sure about it. Okay, so how to tell compiler arrays aligned? Yeah, we're going to come on to that. I'm going to come on to that shortly. So bear with me for a moment. Okay, so here's another example of something that doesn't vectorize. Okay, so if we look at the inner loop here, which is what the compiler will try to vectorize, then we have a scalar x, which is incremented by an array element. So there's this. So each the value of x in each loop iteration depends on the value in the previous one in a non-trivial way. And so it's not possible for the compiler, typically not possible for compilers to generate vector instructions to this because of the dependency on x. So something that you could one way you could deal with that here would be to expand X into an array where you have a different element corresponding to every value of the outer J loop here. So you could basically initialize all the values of the array version of X and then use them inside the loop here. And then in that case, both these loops will vectorize successfully. So in this case, this is an example of what the Cray HList, so this is Cray compiler, Cray Fortran compiler with minus HList equals A will produce for you. Okay, so it marks up the loop, and you have to kind of it does kind of little annotations, but it also tells you in sort of text, you know, and it says basically. Outer loop wasn't vectorized, okay. The inner loop was unrolled, okay. So it succeeded in doing unrolling, but it says it was not vectorized because recurrence found on X at line 19. Okay, so it's pointing you at the variable and the line number that's causing it the problem. And then if we do this, do the promotion to from X from a scalar to a vector explicitly, then we will. It tells it what it's up to. Okay, so it's actually done a reasonable amount here. It's also done some. So with this, it's done some interchanging, and it's also fused with this loop, so it's fused the two loop next together and then vectorized both of it as well as doing the unrolling. So this is basically tells you that it was successful, and it goes well a bit faster. Okay, it's 37% faster. Okay, so yeah, let's come on to alignment. Aligned data is basically essential. If we have problems, if we have unaligned data like this, okay, so if this is a cache line here at the top, and our array is not aligned with the array starts somewhere in the middle of the cache line and not at the beginning, then the compiler has to generate a whole bunch of instructions to try and extract these 8 elements and store them in the vector register. Okay, so it might require, so it's going to require some extra data loads, and it will basically it can also generate additional versions of a loop. Okay, so it'll basically sort of run the loop up to the point where it has it'll generate special code for the first iterations or the last iterations, which don't until it gets to the cache line boundary, and then carry on and so on. If we have the aligned data though, then we'll basically minimize the number of loads and the number of instructions required to sort this out. Okay, so yeah, just to repeat again, yeah, aligned data is best. For AVX, we want things aligned on 32 byte boundaries, and need to say let the compiler do it itself, or tell them what it is. And again, unit stride is best. Okay, so various ways to align our data. So if it's, depending on what kind of data it is, if it's dynamically allocated, then we can use the mmmalloc library instead of plain old malloc. Okay, and then basically there's an extra parameter to basically tell it to tell it what to do. Can also have the in Fortran the align attribute. So if we have allocatable array, and then we can basically say, okay, please align array. When you allocate array, please allocate it in such a way that it's aligned to a 64-byte boundary, for example. For static arrays, okay, there's syntax for C, and then also the same, so different syntax for C, basically the same one as for allocatables for static arrays in Fortran. If you're dealing with old-fashioned Fortran that has common blocks, you can't align data inside a common block, essentially because common block is by definition contiguous storage. You can align the start of a common block, but not the individual arrays inside them. So it's basically you have to, if you want to align the stuff inside, you have to add explicit padding in between. If you have derived types, so in Fortran you can use the sequence keyword. So that basically says it tells the compiler that it must organize the data structure in the order that it's specified, and then do some manual padding. C is a little bit more tricky. You kind of have to rely on the compiler not reorganizing the order of elements of structures for you. You need to think a little bit more carefully, perhaps, if you have multiple dimensional arrays. If you do an mmmalloc for each dimension, then that should be fine. But there are reasons why you might not want to do that. There are reasons why you may wish to malloc the entire multi-dimensional array in one go. So, for example, if you want to use MPI derived data types, and you want to guarantee there's a fixed stride across the dimensions, then you might want to do a single allocation. But then you can run into problems if the dimensions don't divide, aren't nice multiples of the vector length. So you can. So if I have basically a 16 times 5 data structure, then you can run into problems because the inner loop isn't the right length for everything to be aligned nicely. Okay, so for non-static data, as well as doing alignment, we also need to tell the compiler that it's aligned. There's a number of different ways of doing that. So for data that's inside a loop, we can just say, okay, if we know everything's aligned, then we can say just pragma vector aligned or exclamation mark $ vector aligned, and that says basically everything is everything that's being accessed inside this loop is aligned. Or we can do it individually for individual arrays. You can also tell the compiler about values of scalars which are used in indexing. So, for example, in this example here, where there's an offset going on, you can say basically you can tell the compiler that n1 is a multiple of 16. say we'll come on to OpenMP stuff as well, but with OpenMP SIMD directives, you can also say there's a slightly different syntax, but you can also say, okay, the array A is, you can say aligned A64, which says I guarantee that that A is aligned on a 64-byte boundary. Okay, Fortran, yeah, okay, so I have to think a bit carefully about how we pass data into subroutines, because that affects what the compiler does and doesn't know about the alignment. So if we have to have explicit arrays, okay, so where they are, where the dimension is explicitly declared inside the subroutine, that's fine. But the compiler, what the compiler will generate code is assuming that that is contiguous data, and any packing or unpacking required to do that is done by the compiler. There's obviously going to be some overhead associated with that if you try and pass in non-contiguous array subsections, for example. And then basically you need to tell the compiler that these things are aligned, because they're coming in through the argument list. The compiler doesn't know anything about what you're passing in here. You could be passing, what you pass in is this could be, some arbitrary element of an array in the calling routine. So the compiler has no idea about the alignment here. So you're going to have to tell it. And it's basically the same deal. If you pass, also if it's not explicit here, if it's passed as an argument through the routine, it's the same deal. Okay, so then we can have assumed size arrays. So if you just specify a colon as the dimension here, then the compiler will generate different versions of the code for contiguous and non-contiguous data. So it'll generate a fallback version. So it'll try and choose what version it needs to use at runtime, but you still need to tell the compilers about the alignment. Okay. And pretty much the same for assumed shape arrays as well. Okay, yeah, indirect addressing as we've mentioned before, can be problematic, and so have indirect addresses like this, then we need to basically tell the compiler that it's independent. It will generate gather and scatter operations to pack and unpack the index locations into the vector registers. If we use array syntax here, then this will actually create an array temporary for the right-hand side evaluation. So this will typically end up effectively doing this. It'll basically create a temporary with the result of the right-hand side, and then so this will end up effectively creating two loops rather than one. Okay, so what we've seen so far is mostly the sort of compiler-specific directives for vectorization, which is fine, but it's not very portable. So OpenMP, as of version 4, contains a standardized set of directives. they don't have a great deal to do with the rest of OpenMP. There's a couple of concepts. There's things like reduction variables that carry over, but it was just considered that OpenMP was a convenient place to was a convenient standard to use to standardize this stuff rather than create a whole separate standards body for it. Okay. So the way this works is, okay, so there's a SIMD directive which says vectorize the loop. Okay, so this is the way to tell the compiler that it's okay to vectorize. So it's basically hash pragma OMP SIMD or Fortran $OMP SIMD. So that immediately precedes the loop. So that says, please execute the iterations of the loop in SIMD chunks. This does not do loop parallelization across threads. Okay? You can combine this with loop parallelization across threads, but this is just doing the vectorization. Yeah, this is essentially says this is not a hint. Okay. This is really an assertion of the independence of the iterations. So if you get that wrong, you'll end up with code that produces wrong results. So we have sort of clauses on the end of the SIMD directive which control the data environment and how the loops partition. So there's various clauses. You can limit the number of iterations in a SIMD chunk if there's some long distance dependencies, for example. Dependencies not on the previous iteration, but on the iteration the iteration 5 before. Then you can say, well, it's okay to do 4 chunks of 4 in SIMD. There's a way of dealing with induction variables. Okay, so the linear clause, you can list variables which have a linear relationship to the iteration space. So things which are incremented by a constant amount in every iteration. You can just list those in a linear clause, and the compiler will deal with those for you. We've already seen the alignment. Okay, specify byte alignment. So other things like privates, so data scoping, private, last private, reduction, so you can handle reduction variables, and you can also do loop collapsing. Okay, so you can, if you have a loop nest, you can use the collapse. What the collapse clause does is will unwind the loop nest into one long loop. And basically vectorize that instead of just the innermost loop or the loop that we're applying the directive to. So also you can, under the right conditions for the right kind of function, you can also persuade the compiler to generate SIMDized versions of functions that are called inside the loop. Yeah, okay, so then there are combined ones. If you want to parallelize across threads and vectorize, you can use combined directives like OMP4 SIMD. So most compilers these days do have support for the OpenMP directive set. So that's quite useful in the sense that it allows you to do this reasonably portably across different compilers. Okay, any questions? Okay, so I suggest we'll take a short break for about 5 minutes or so before I start the next section.